It is everybody's favorite time of the cryptocurrency year. It is hard fork time. Ethereum is going to be hard forking in a couple of weeks as part of a planned network upgrade. When Ethereum was first conceived, it outlined a series of milestones for future development. The Olympic testnet launched in May 2015. The Frontier release took place on July 30th, 2015, and was the first deployment of the main Ethereum network. The Homestead upgrade went live on March 14th, 2016, and now it is time for Metropolis. Now, EIP86 for account abstraction, which is one of the most interesting pending changes to the Ethereum protocol, was intended to be part of the Metropolis release, but it isn't finalized yet, so the development team is splitting the Metropolis milestone into two separate releases, codenamed Byzantium and Constantinople. The first part of Metropolis, Byzantium, is set to go live at block number 4,370,000, which is going to happen on October 17th. Byzantium is bringing with it some new toys for smart contract developers in the form of 4 new EVM opcodes and 4 new native contracts, as well as some modifications to the difficulty adjustment algorithm and transaction receipt data. I'm going to take a more in-depth look at all of these changes right now. To start, the EVM is getting 4 new opcodes: Revert, return data size, return data copy, and static call. Let's kick this off by taking a look at Revert. Okay, so I'm going to pop into Remix for 1 second, and I'm going to make a super simple contract that I'm going to call Byzantium. And all this contract will do is have one function called hello that will return a string. And all that this function will do is return hello from Byzantium. But I only want this function to return this string if we're actually on the Byzantium fork. So I could check and have a little guard that says if block.number is less than 4,370,000, then throw. And I'm going to add a pragma mark for the version of the Solidity compiler which I'm using, which I'm going to start on 0.4.9 for demonstration purposes. Okay, so what is this actually doing? So when you use this throw keyword in Solidity, what this is actually doing is it's compiling down into an invalid jump exception on the EVM. And the invalid jump exception, when you encounter it, will revert all your state changes of your contract execution. It will fake an infinite loop that consumes all the gas that you sent to the contract execution, and it will error out. And it does work, but it is a bit of a hack, and it has 2 real issues with it. First and foremost, it uses all the gas that has been sent to the contract execution. And you might think it's not that much money, but for some of these land rush ICO contracts that have happened over the past couple months, people will set really, really high gas prices, and they'll lose something like $15,000 that they spent trying to get into some sort of ICO, but they don't get in time, they encounter the throw, it makes the invalid jump, uses all their gas, and they lost $15,000 and got nothing for it. So, I mean, there are issues with the contracts consuming all the gas, but even more importantly than that, perhaps, is that when you use all the gas, you don't have any gas left to return any data, so you don't have any error messages. So up until now, there have been no real error messages from smart contracts, which any developer knows has been a really massive problem in the workflow of developing these things. So Solidity 4.10 introduced a slightly new syntax for handling exceptions. Instead of doing this if block.number is less than 4.37 million, we could just assert that the block number is greater than 4.37 million. And we'll see that this doesn't actually compile because I'm on version 4.9 of the Solidity compiler, and I just wanted to prove that this was actually introduced in 4.10. So if I slightly bump the version of the Solidity compiler that I'm using, this should compile fine, and it does. So in Solidity 4.10, they introduced this assert syntax, and we could assert that the block number was greater than this, and that would have a very similar effect. The difference, though, is that if we look at the actual compiled bytecode for this contract, I'm just going to copy it into IA Writer right now, and we search for OXFE, we'll see that we have this opcode right here, FE. Ignore the first 3 on the top, those are from something different, but this opcode right here, OXFE, is from this assert statement. And what's interesting about opcode OXFE is that it doesn't exist. So if we look at the yellow paper and we look at all the opcodes that are defined in it, OXFE is not defined. This is not a real opcode, and this is done intentionally. The assert statement, the entire point of it is that it's going to compile down into an invalid opcode exception, which will have exactly the same functionality as the throw statement. It'll use up all your gas, and it will exit from the contract, but maybe in a slightly nicer syntax. But Solidity 4.10 also introduced the require function. Require has a very similar syntax to assert. You just put require and then some sort of truthy statement. But if we look at the compiled bytecode from this contract now, and we paste it in here and search for FE, we'll see that that opcode FE is gone. So it's compiling to something different. And it's actually compiling to OXFD instead of OXFE. And if we look at the yellow paper, we will notice that OXFD also doesn't exist, but it is going to. So starting in Byzantium, we are going to have OXFD, which is opcode revert. And revert is going to halt execution of the EVM without consuming all the gas that was passed into the contract. So if you had been using Solidity 4.10 or higher and had included this require statement, at any time in your contracts, this will, starting in Metropolis, it will stop using all gas when this error fails, and it will start refunding your gas, which is really, really cool. Because this gives back the gas, you could almost say it is always better to use a require statement than an assert statement, because again, this will refund gas. But where this gets really cool is that because the require statement and the revert opcode are not using all the gas of the contract, you're going to have other gas left over to maybe return an error message. So if we go back to our yellow paper and scroll up to the 30s, we'll see that we have these opcodes right here, call data size and call data copy at 36 and 37. And you know, what call data is when you have a function in a smart contract and it takes arguments like x, y, and you call this with two parameters. Those x, y arguments are what's called the call data of the function, and that comes in as some buffer to the contract. And the way that you are always dealing with things in the EVM is that you have some start byte, which we'll just call x, and then you're going to always be copying bytes from that buffer onto the stack. And you're going to copy n bytes from the start byte. So you always need these kind of opcodes like call data size to get the size of the call data, and then you're going to copy from x, you're going to copy n bytes from x. So these kind of things play in tandem with each other. But this has worked really well for smart contract developers, not necessarily using the raw opcodes. They use things like Solidity, but they've been able to deal with function parameters. But they haven't really been able to deal with the return data. And the return data behaves very similar to this call data, where you have some sort of buffer of return data, and you might want to copy it onto the stack to do things with it. So you need to know how big it is, right? So you need something like call data size, and you need something like call data copy, so that you can manipulate the return data and do things like error messages. So what's going to happen is we're going to have two new opcodes. We're going to have return data size, and we're going to have return data copy. And these are going to behave exactly the same way that the call data opcodes do. So this is kind of like battle tested already. But these two things in tandem are going to allow error messages to exist. And when we go back to Solidity, most smart contract developers aren't going to need to deal with the opcodes. They're just going to deal with something like Solidity. And Solidity will eventually, it does not right now, by the way, you won't be able to use error messages once Byzantium launches, but in the next version of Solidity that's going to come hopefully soon, I think you'll be able to do something like this. So you'll have a statement like require, and then you can have some sort of truthy test, and then you'll have some sort of error message like block is not high enough. And you'll have some sort of syntax like this that will basically leverage those opcodes and let you have error messages should some sort of condition fail. Also, unrelated to the error handling, there's also a fourth opcode getting added in Byzantium, which is OX4A, and that is going to be static call. Static call is a way that you can call out to other contracts and execute code with the explicit declaration that the execution environment cannot modify state in any way. And this is to prevent a large class of reentrancy bugs that have been happening or have been proven to happen on Ethereum. And it's going towards this thing called CQRS, of command query responsibility segregation, where you just have different paradigms for executing commands, which are things that modify state, and queries, which are things that are read-only. And having an explicit opcode for calling out to contracts in a read-only context is really valuable because it makes it a lot more obvious what code is doing, and it lets high-level languages like Solidity implement features like what they're going towards in the next release, which is going to have this pure declaration where you can define functions as pure functions that don't modify state. So these are going to be tools for developers to use just to make it a lot more obvious what contracts and functions are actually doing, and hoping to prevent reentrancy bugs and et cetera, things that have been happening on the network in the past. Ethereum is also getting 4 new native contracts. So what is a native contract? The EVM is a Turing-complete computer, meaning that in theory, it can calculate any arbitrary computation. But in practice, it's actually a very slow and inefficient computer due to the trade-offs it makes for decentralized execution. So there are some bits of math that require performant execution or large memory that you might want to actually execute inside of smart contracts, such as functions related to cryptography. Let's look at an example of this. Say, for example, that you wanted to calculate 17 raised to the 800th power mod 133. Well, this is a class of problem called modular exponentiation when you raise some number to a large exponent and then take the mod of that number. And the resulting number from this equation is going to be really small. It's going to be at most 3 digits long. But if you think about the way that you would actually go ahead and calculate this, you would first raise 17 to the 800th power, and this intermediary state is going to be really, really large. This is actually going to be like 985 digits long. And then you're going to take the mod of that really long number and arrive at the really small solution. But this intermediary state, you can't store this in memory on the EVM. It's really expensive to store something 985 digits long in memory. And fortunately, there are algorithms for doing modular exponentiation where you don't need to store that big of an intermediary number. But those algorithms are inefficient to run on the EVM. So something like modular exponentiation is a really important base primitive for cryptography, but it's hard to actually execute this efficiently on the EVM. But what you actually can execute it efficiently on is the CPU that's running the host node. So for example, there could be a really efficient algorithm written in Golang, which is the programming language that Geth is written in, and they could execute modular exponentiation really efficiently. So here's the idea behind the native contract, is that you'll make some address, let's say like 0x00 dot, and these are all zeros, all the way into 05. And at this address, you're going to hard code into the Golang client. You're going to say, if anybody ever makes a call to this contract, instead of actually finding the contract that's deployed at this address, we're just going to hard code the algorithm for modular exponentiation at this contract address. So you could effectively pretend as if you're executing this function on the EVM, but really you're executing it in the client itself. And then the client will execute efficiently the modular exponentiation and return the result back into the execution environment of the EVM. So you effectively get this functionality inside of a smart contract. And if you wanted to actually look at these precompiled contracts, we can go into the codebase of Geth at go Ethereum core vm contracts.go, and we'll see a list of precompiled contracts right here. There's 8 of them total. There were 4 of them before Byzantium. 4 are getting added for Byzantium. They're all cryptography functions for EC Recover, SHA-256, RIPE-MD 160, and then the ones getting added in Byzantium. And then the implementations are down here later in the file. So the precompiled contract at 0x05 allows for efficient big mod exponentiation, which will allow for efficient RSA verification inside of smart contracts. Okay, but what are these other contracts? So the 0x07 and 08 contracts are going to all deal with elliptic curve cryptography functions. So just a quick primer, an elliptic curve is something that satisfies the equation y squared equals x cubed plus ax plus b. And if we drew out what one of these things look like, they look something like this. So here's an x and a y axis, and this will just be a simple example of an elliptic curve. It'll look something like this. And there's a couple interesting properties that curves like this have. And the first property is that if you make 2 points on this curve, so I'm going to just draw 2 points here. I'm going to call this one P, and then I'm going to draw a point here, and I'm going to call this Q. If you draw a line between P and Q, so through P and through Q, it will always intersect the curve at another point. We'll call this negative r for now. And that point will always be on the same side of the axis as the p and q. So if p and q are both above the x-axis, negative r is above the x-axis also. And then the curve also has a property that if you reflect the point on the axis, it will always intersect the curve at another point underneath it. And we'll call this point r. And these two properties give elliptic curves very interesting cryptographic properties. But this idea of taking p and q and then finding the r point is something that we call point addition. So point addition. And point addition is p plus q equals r. And the precompiled contract at 0x06 in Byzantium deals with doing point addition on elliptic curves. So let me go ahead and rewind this elliptic curve back to the beginning. Something else you can do that's interesting also is if you just have one point only, so let's just say we have p, there will always be, a tangent line. So like the line that is tangent to that point. And that tangent line will always intersect the curve somewhere also. So I need to make my curve a little taller here, but the tangent line will always intersect the curve somewhere. So you could call that point negative r and then reflect it down to find your r point. And this is effectively doing p plus p, or 2p, when you just have one point and you're finding the r point of that one point. And then you could do the exact same thing again. You could find, the line tangent to this point, find that point, and then reflect it to find the r point. And then this r point here would effectively be p plus p plus p, or 3p. And this idea of repeated addition of one singular point is what we call scalar multiplication. So scalar multiplication, and scalar multiplication is what 0x07 precompiled contract is going to deal with. It's going to give primitives for doing scalar multiplication on elliptic curves. And then the 0x08 contract is something called EC pairing. And I'll have to admit, I do not actually really understand what this does, but it is some cryptographic primitive involving elliptic curve cryptography. And the whole point of adding these precompiled contracts is that the elliptic curve cryptography is what underlines the zero-knowledge proofs. So Ethereum wants to add capabilities to be able to do zero-knowledge proofs, and it needs this kind of cryptography in order to enable them. So you might have seen this story go by that somebody verified a Zcash transaction from inside of an Ethereum smart contract. This is how they were doing it. They were using these native contracts that were added in Byzantium in order to relay out to this kind of cryptography and verify the zero-knowledge proof of Zcash. Byzantium is also bringing with it adjustments to the difficulty adjustment algorithm. Okay, what is the difficulty adjustment algorithm? Well, when you mine a block on a blockchain, you need to mine it with what's called a nonce, which is just some arbitrary number that is really, really big, and then you hash that number against the contents of the blocks to produce what's called a mix hash, which is some random number that you can't possibly anticipate in advance. And then that number has to be smaller than another number, which we're going to call the difficulty. And this is going to be some really small number, like starting with a lot of zeros, 1. And then if your mix hash is less than the difficulty, then congratulations, you have successfully mined a block and you can broadcast it to the blockchain. Well, with something like Ethereum, they try to have really fast blocks, and I think the average block time is around 12.5 seconds per block. And in order to keep that consistency, when you have a blockchain, when you mine a new block, you can look at the timestamp of all the, like the most 10 recent blocks and get an average timestamp of that. And if, for example, the average block time of the last 10 blocks is only 10 seconds, well, then you can take the difficulty and you can adjust it upwards, which means that this number becomes a lot smaller, and then it's thus harder to mine a new block, which means that for the amount of hash power on the network, which must have increased to get 10-second block times, now the difficulty has increased in concordance with it, and the block time should start increasing again back to 12 seconds. Likewise, if the average of the last 10 blocks was 15 seconds, a miner could adjust the difficulty downward. And the way that this works is that each miner has an opportunity, whenever they mine a block, to adjust the difficulty slightly up or slightly down at each block. And the adjustment algorithm that they use is hard-coded into the clients themselves, so it's hard-coded into Geth and Parity. And the miners will use that, and they'll just have an algorithm running to adjust the difficulty based on the timestamps of the most recent blocks. And just for an analog, in Bitcoin, every 2 weeks, they will have a difficulty adjustment period where they'll adjust the difficulty for the timestamps of the blocks on the network. But every 2 weeks gives people opportunity to kind of manipulate this because they can prepare in advance for it. So the fact that Ethereum does it after each block, I think, in my opinion, is a slightly better system. But anyway, right, these are hard-coded into the miners. So one thing to note, when you have a short block time, like 12.5 seconds, you have a centralization risk due to latency. So for example, if a miner, big mining pool, mines a block, well, they need to broadcast that block to the entire network. But say, for example, that the latency on the network is 2 seconds, which is not that much time. But if the block time is 12.5 seconds, well, then the latency is 15% of the entire block time to mine the next block. So this miner would have a 15% advantage looking for the next block because the latency for other miners to receive his valid block. So you have a centralization risk of people taking advantage of this latency when you have small block times. So Ethereum has this thing called the Ghost protocol, which is part of the initial Ethereum spec. And the Ghost protocol has these things called uncles. And the whole point of uncles is that if you mine a valid block, but it doesn't make it into the main chain, you can still include that in the block of a block that's on the main chain. So a miner can look at an uncle block, which is a valid block that's been broadcast to the network, but didn't make it into the main chain. And then he can include that in his block, and whoever mined the uncle block will get 7/8 of the mining reward, which up until Byzantium was 5 ether. And the miner that mined the uncle block into his block on the main chain will get 1/32 of the mining reward of 5 ether as an incentive for him to do it. And the whole idea here is that including these uncle blocks adds security to the network because all this hashing power that went into it is included in the main chain, and it would make a 51% attack that much harder. But it also kind of mitigates against this latency attack where miners that are mining valid blocks but maybe a little late to get in the main chain are still getting mining rewards from it. But anyway, the whole point of what I'm getting at here is that the uncle blocks affect the disbursement of new ether because there's new ether being generated for all of the uncle blocks. But as I said before, the difficulty adjustment algorithms that Geth and Parity are using are only taking into account the timestamps of the blocks. They're not actually taking into account the uncles. So the difficulty adjustment algorithm is adjusting for blocks on the main chain, but it's not adjusting against the disbursement of new ether. So there's going to be a change in Byzantium to modify the difficulty adjustment algorithm to take in account these uncle blocks. And what that's going to do is that's going to make the difficulty adjust in concordance to the amount of new ETH that is actually being manufactured. So that means that the inflation rate of Ether will actually be controlled by these difficulty adjustment algorithms as opposed to just the timestamps. And that can mitigate against potential attack vectors with people manipulating the uncle rate and the difficulty adjustment together to try and game the system somehow. Byzantium is also going to be delaying the Ice Age. So what is the Ice Age? So we said before with that difficulty adjustment algorithm that is going to adjust up or adjust down the difficulty to target a block time of 12.5 seconds. Well, there's something that's hard-coded into the clients themselves called the Ice Age or the difficulty bomb, which says after a certain block number, so after a certain block number, then the difficulty adjustment algorithms will not adjust for 12.5 seconds, but they will start adjusting for higher and higher block times, so 14-second blocks, and then 18-second blocks, and then 25-second blocks, and then 30, et cetera, et cetera. And this period where the block time increases exponentially forever is called the Ice Age. And the reason that the Ice Age is coded into the clients is so that when Ethereum does have hard forks, for example, this Byzantium hard fork, that miners will be incentivized to actually upgrade their clients. Because if they don't upgrade their clients, this difficulty bomb is hard-coded into it, and it's going to make it infeasible for them to keep a legacy chain going. And this is a way to kind of provide an incentive for all miners and all people running the Ethereum network to upgrade, or else they will never get new blocks and no shenanigans can be played. And this obviously is in direct response to Bitcoin, which has notoriously hard problems upgrading the network. Now, what Ethereum is going to be doing in Byzantium is that they are going to be delaying this ice age. They're going to be hard forking the code base so that the difficulty adjustment algorithm goes back to 12.5 seconds, and they're going to delay the ice age because we're currently in the ice age. So they're going to be pushing it back 1.4 years. And the idea of 1.4 years is that will probably be around the time of the next hard fork, which will probably not be proof of stake, but it'll probably be the last hard fork before proof of stake. So this is going to be a really important point in 1.4 years, but this hard fork is going to be delaying the ice age. Byzantium is also changing the base mining reward from 5 ether to 3 ether. Okay, so why are they doing this? Well, the public justification is that because the ice age is getting delayed, that the mining reward should be deduced in concordance with that. And for example, if a miner had been making calculations on how much ETH they should make before the change to proof of stake, they would have assumed that the deadlines that the Ethereum Foundation set out for proof of stake would have been met. Because Metropolis is being split into 2 hard forks and the ice age is being delayed, the miners would actually be making more ether than anticipated because it's going to take longer to get to proof of stake. So they're saying that, well, we'll just reduce the base mining reward so that miners will be making the same amount of total ether as they would have anticipated. I do not know how much I kind of buy that explanation. I mean, in my opinion, the reason why the development team wants to reduce the mining rewards is because they want to keep the miners on a bit of a leash. You know, when Ethereum is going to move to proof of stake, this is still maybe like 2+ years away, in my opinion. So when they move to proof of stake, miners are going to start going from making, you know, real money to making 0, right? Like their mining equipment will not work on the proof of stake network. So, I mean, there might be like a hybrid transition where it's hybrid proof of work, proof of stake for a while. So maybe it might not be that extreme, but they'll, you know, lose a lot of money. So if the miners so the price of ether, right, at the last hard fork was around like $10 per ETH, which means if you were mining, you know, 1 block a day, you were making $50 a day. But now, with the current price at like $300 per ETH, miners are making, if they're mining 1 block a day, they're making $1,500 a day. And that's serious money. That's like $500,000 a year, right, in revenue. So they are worried that miners are going to be making so much money that when they try to switch the network to proof of stake and take a hit against that, if you're dealing with this much money that miners are making, there might be some serious conflict moving the network to proof of stake. Because again, it's so much money that you stand to lose. So I think that the Ethereum team is thinking about, well, if the price of Ether continues to go up, we really need to do something about these mining rewards so that we're not in the situation that Bitcoin is in, where the miners are holding the network hostage constantly and nothing can get done. So I think that they're just seeing this as an opportunity where it's like, all right, well, we're making a change now. Proof of stake is a couple years away. Like, let's just sneak this in. Let's get this reward down immediately just to show the miners that we have them on a leash and that we want to preempt any problems that are going to happen with the proof of stake release in 2 years. So this is going to be an interesting, it's going to be an interesting thing to see how this plays out, but they're going to be reducing the mining rewards from 5 to 3 ETH. Okay, one more thing to talk about. Let me fire up Infura, and then I'm going to go to Etherscan and just go to the latest block that was mined and just get some random transaction out of that. So 105 transactions, and then this, and then I'm just going to grab the TX hash. And then I'm going to do web3.eth.get transaction receipt, and then paste in that TX hash. And I get all of this stuff here. And we're going to take a look at this field called root right here. So what is this? When an Ethereum block gets mined, it has a bunch of transactions, right? TX, 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 TX. And after each one is processed, it generates a new node in the state tree. And then the state tree is a Merkle tree, so it hashes all the nodes together and arrives at what's called the root, or the state root, when we're talking about the state tree. And then that state root is added to the TX receipt that you see here. So each time that a transaction is processed, it generates a new node in this tree, and then that new Merkle root is added to the TX receipt as this root here. Well, the problem with this is that this root parameter right here is actually the only dependency that a transaction receipt has on other transactions within the same block. So this transaction here needs to be processed after this transaction here because it needs to know about this transaction's intermediate state root in order to generate its own intermediate state root. And then at the end of the block will have one root parameter, which is the root of the state tree after the entire block has been processed. But in practice, you very, very rarely ever use these intermediary state roots from an individual transaction. You're more concerned about the root after the block. And what this means, having these intermediate state roots, is that this entire block, all of the transactions in the block need to be processed in serial because you need to know about the intermediate state root of each transaction in order to generate your own. But if you removed this parameter entirely from the transaction receipt, well then that would open you up to being able to process all of these transactions in parallel, which means that you could process, if you had 8 transactions in a block, you could process all 8 transactions simultaneously on 8 different threads in your computer and potentially get an 8x performance boost of how the EVM was working. So this is a really interesting idea, but it would require removing this state root parameter and require a couple other modifications. Well, first and foremost, for backwards compatibility reasons, it might be a bad idea to actually remove the state root parameter entirely. But what's going to happen starting in Byzantium is that if the state root parameter is just going to become a binary digit, so it's going to be 0x0 if the transaction had failed, and it's going to be 0x1 if the transaction succeeded, but you're not going to have these intermediate state roots, which means you're going to open up the block for parallel processing. Also, in order to make the parallel processing work correctly, you're going to need to add new parameters or new optional parameters into transactions. So what they're proposing doing is adding new parameters called read range and write range. And these are going to be basically whitelisted addresses. So they could be contract addresses or account addresses. And they're just going to be addresses that you pass into the transaction. And you're saying these are the only addresses that I'm interacting with. So if you know you're only sending Ether to one address, that would be in your write range. Or if you're just calling a contract, that could be in your read or write range, depending on what the contract is doing. But you just pass in all the addresses that you're interacting with. Then the nodes can look at them. And if there's 4 different transactions, and those 4 transactions all use different addresses, well, guess what? You can process them in parallel because you know that they're not going to conflict with each other. And then what's going to be super interesting is that there's going to be a gas incentive for actually processing transactions in parallel. So using these new APIs to process transactions will have gas incentives. Because in theory, right, you're getting an 8x performance boost, and you want to incentivize users to make transactions in specific ways where they can make use of those performance boosts, because scalability is going to become, the big hurdle on whether or not Ethereum succeeds or fails. So let's actually look, because Byzantium right now, right, is deployed on Ropsten, so we should be able to see this. So if I exit out, and instead of going into mainnet, I go to Ropsten, and then I copy my all ones little private key that I have over there, just so my thingy starts up. And then I go to Ropsten Etherscan, and let's look at the latest block that's been mined, and there's 13 transactions, and let's just grab the TX ID of one of them and throw it in here. So we'll do web3.eth.get transaction receipt, and then pass in that TX. We'll see that this root, this little root parameter right here is empty, because that is being removed in the API for the transaction receipt data in Byzantium. So to the best of my ability, that is an overview of the changes that are coming in Byzantium. If you like this kind of content, please let me know. Drop a comment on YouTube or on Twitter. It really does make a difference when I hear from people that they like these kind of videos. So anyway, the video's done. Thank you.